Good morning, everybody. So today we're going to look at the last section in Chapter 2 on motion. We're going to specifically be looking at acceleration. Now, I know you've heard that term before. Now we're going to get to learn about what it is, how it works. So, acceleration. The main idea of this section, let's write it down, is that acceleration, you like my purple pen? Acceleration describes how the velocity of an object is changing with time. Okay, in other words, it's what happens when you speed up or slow down. Okay, so acceleration. Let's make sure we understand what it is. When we look at acceleration, acceleration is designated with the lowercase letter A for acceleration. And it is a rate. And guys, we have talked about the term rate before. Okay, a rate is any ratio, and you all know what a ratio is. It's one number divided by another. It's any ratio with time in the denominator, the bottom part, in the denominator, the bottom part of the ratio, all right? So it's the rate of change in velocity, okay? So I'm going to make a ratio. Acceleration is the rate, time in the denominator, of change in velocity. That can be written as a delta. Delta V for velocity. Delta means change, and mathematically, delta means subtract. It's like mathematical shorthand, okay? So, when we subtract, we're going to say the final velocity at the end of the time period minus the initial velocity at the beginning of the time period divided by that time period. So this is how we're going to find accelerations. This is a rate, the rate of change in velocity from one value to another. In fact, when you subtract, you'll get an increment. And acceleration is the increment that you're going to add or subtract to your velocity each second, okay? The increment of change each second. Let's look at an example. Oh, wait, we got to talk about the SI units first, don't we? All right, so how do we measure acceleration? Well, in order to find the units that we're going to use, we have to look at the formula. We know that speed and velocity are measured in meters per second, okay? And we're going to divide that by time, which is measured in seconds. So we get a meter per second, or a meter per second each second. And we can actually combine those two, and it would be meter per second squared. A square on the S. So this is the SI units right here. Don't forget that. That's how you're going to be able to identify it in a problem. Notice, the velocity is on a lower level than acceleration. It only has one S. Acceleration has two S's, S squared. Okay? Keep that in mind. Now let's look at how acceleration works. If your acceleration increment, the increment you're going to change your velocity by, if it goes in the same direction as the velocity, if they're both positive, in other words, then you'll speed up. Your velocity gets bigger and bigger every second because you're adding an increment to it. So, for example, let's suppose we had an acceleration of 2 meters per second squared, and the car starts at rest. Okay, the initial velocity equals 0 because you're at a red light, and then it turns green, so you're going to accelerate forward at 2 meters per second squared. Since your velocity and acceleration go the same way, we're going to add the 2 to the velocity. Well, our initial velocity is 0, so at the end of the first second, our new velocity is going to be 0 plus 2 is 2 meters per second. Okay? At the end of the second second, we're going 2 meters per second. We're going to add an increment of 2, so now it's going to be 4. At the end of the third second, we're going 4. We're going to add 2, so it's going to be 6. You get the idea? The fourth second would be 6 and 2 is 8. And the fifth second would be 8 and 2 is 10 meters per second. Okay? Now, that means that the increment of change in velocity, final minus initial, 2 minus 0 is 2. Final minus initial, 4 minus 2 is 2. Final minus initial, 6 minus 4 is 2. Final minus initial, 8 minus 6 is 2. Final minus initial, 10 minus 8 is 2. So 2 is the acceleration increment you're changing your velocity by each second. Kind of cool, huh? Now, that's what happens if you're accelerating, if you're speeding up. But what if you're slowing down? Well, there is another name for acceleration when you're slowing down. A lot of times they call it deceleration. It just means that your acceleration actually points... Oh, hang on just a minute. Announcements. Ugh.
We will be locking the front doors in just a moment.
Yeah. Okay, so now we can get back to this. All right, so deceleration is simply when the acceleration points opposite the velocity. Well, if we take the forward motion of the car to be positive, then the acceleration or deceleration is going to be negative, okay? And see, look, the car is coming to a stoplight, so he has to decelerate or slow down to a stop. All right, so let's take a look. Let's suppose that we have an acceleration rate of negative 2 meters per second squared. And let's suppose we start with an initial velocity of 10 meters per second. Well, at the end of the first second, how fast is the car going to be going? You know, when he hits the brake right here, how fast is he going to be going at the end of 1 second? Well, 10 minus 2 is 8. All right? And how fast is he going at the end of the next second? Well, 8 minus 2 is 6. How fast is he going at the end of the third second? 6 minus 2 is 4. And then the fourth second, 4 minus 2 is 2. And finally, the fifth second, 2 minus 2 is 0. And he's stopped. Let's hope it's at the light. So, acceleration, you're going to add the increment to your velocity. Deceleration or negative acceleration, you're going to subtract the increment from your velocity so that it gets smaller. Okay? Now, the interesting thing about acceleration, is that acceleration is a vector. Notice we can use an arrow to represent it, just like we do with velocity. That means it has direction as well as magnitude. The numerical value is the magnitude, but it also has direction. And here's the interesting thing. An object can be going constant speed, not velocity, constant speed, and still be accelerating, because velocity has both magnitude and direction as well. And if you're changing either part, the magnitude or the direction, then you have an acceleration, okay? So, an acceleration can mean a change in the direction of velocity too. Okay? So this car going around a circular track, It may be going at constant speed, say 50 miles an hour, but because the the direction of the velocity is changing, it is also accelerating. It's just that it's the direction part that's changing, not the numerical part, not the magnitude part, okay? And we'll be talking some more about that shortly. So acceleration means a change in velocity. It can be a change in the magnitude or a change in the direction. Now, we can also look at acceleration on a graph. If you take a graph of either speed or velocity versus time, the slope, the steepness of the line, how steep it is, represents the acceleration. Now, how do we know that? Well, let's take a look at how we know that. As you guys know, slope is rise over run. And in math, they teach you that is the difference in the y values of 2 points divided by the difference. Remember, delta means shorthand. It means subtract between the x values. Well, let's take a look. Let's take a look. The y values are the speed. So you're talking about a change in the magnitude of the velocity, a change in the numerical size of the velocity. And the x values are the time. So you're talking about a change in time, a time period. Change in velocity over time, acceleration. That's how we know slope of the line is acceleration. The steeper the slope, the greater the acceleration increment, and the faster the speed changes, okay? All right, so let's take a look at this. Notice we have a lot of things going on. I think this is a student's trip somewhere. She started at home, okay? And she increased speed to 10 in this time period, half a second. Says she's pulling out of her driveway. So she increases speed. That means she's accelerating. And whatever the value of this slope is, that's her acceleration increment. Then, notice right here, the line is flat, okay? That means no slope. In fact, look, the speed stays 10. And if the speed stays the same value, from here to here it's constant speed, there's no acceleration, okay? So, then right here, now she's going from 10 back to 0. In this amount of time, she's going from 10 to 0, so she's slowing down until she stops. Now, she stays stopped for a while. Oh, that's because she's at a red light. How about that? You do stop at a red light. I hope you do anyway. And she stays stopped for a time period. Then her speed increases again. And look at how much it increases over this short period of time, 3/4 of a second. So this is a large acceleration rate because it's a very steep line. Okay? Then she stays at constant speed of 20 for a while. Then she slows her speed down to 10 again, and it stays constant for a short time. And then she goes from 10 meters per second down to 0. She stops right there. In fact, anytime you're on the x-axis, that's where 0 speed is, that's when you're stopped, you're at rest. So, let's actually look at this and make sure we understand. All right, so point an arrow at this flat part. All right, and we're going to say if the slope equals 0, which is what a flat line is, it has 0 slope, there's no steepness to it, then the acceleration is 0. Okay? Because notice it stays a constant value from this point to this point to this point to this point. It's all 10 meters per second. So it's constant. All right? You have constant speed, no acceleration. Now, let's look at this piece right here. Anytime you have a negative slope, so if slope is negative, that means it slants down to the right, okay? If the slope is negative, the acceleration is negative also. And you're going to subtract the increments. That's why the car goes from 10 to 5 to 0 speed, because you're subtracting the increments. Negative slope, You subtract the increments, you get slower. Now let's take a look at this one. This is a positive slope. So if slope is positive, the acceleration is positive. And that means you're going to add the increment to your speed, which makes your speed get bigger and bigger and bigger up the y-axis. Okay? So, positive slope, positive acceleration, your speed gets bigger. Zero slope, all right, means zero acceleration, you stay at constant speed. Negative slope, negative acceleration, you're going to subtract from the speed, your speed gets smaller. Okay? Now, let's look at mathematically how we can solve problems for acceleration. This is actually quite easy, guys. So let's take a look. All right, and if you have a calculator with you, you can check. It says a car is sitting at a red light facing east, okay? And when it turns green. And the car accelerates forward for 10 seconds, and at the end of this time, it's traveling 25 meters per second east. Determine the acceleration of the car. All right, first let's look at our numerical information. Step one, we always identify what we have. Well, 10 seconds, what is that? That's a measure of time. We always measure time in seconds. And then it says at the end of that time, this is how fast it's going. Now notice that says at the end of the time. So that means this would be the final speed or final velocity, magnitude, direction. So this is the final velocity, 25 meters per second east. Well, what was the initial velocity? The car was sitting at the red light. They don't actually tell us, but we can infer that the initial speed is zero because the car was just sitting there when the light turns green and it has to start moving. All right, so we know that. We can infer it from what it says. And we want to determine the acceleration. So we've got the time, we've got the initial and final velocities, we want the acceleration. The formula is acceleration is VF minus V sub I, always final minus initial, never the other way around, ever, divided by the time. Now we're going to chuck in our numbers, okay? The final first, 25 meters per second east minus 0 over 10 seconds. Okay? That gives us 25 meters per second east because when you subtract nothing, you still got what you started with. All right? And 25 divided by 10, then we're going to move, when we divide, we move the decimal back one. So we get 2.5 meters per second east. There's our acceleration. Okay? Notice it is positive. That's because we started from rest and we added these increments, 10 of these increments to get 25. Okay? We went from 0 to 2.5 to 5 to 7.5 to 10. Get the idea? All right? So, now, notice the direction of the acceleration. All right? Oh, by the way, that last part was step 3. Sorry about that. I tend to want to keep writing horizontally out that way for some reason instead of down. Okay, so in any case, notice the direction of the acceleration. All right? Right here, we need to write this down. Direction of acceleration is same if A is positive and opposite if A is, is negative. All right, so we got a positive value. That means the velocity was east and the acceleration was east. That's like this right here. Okay, you're speeding up. But if we had said final minus initial, say you started at 25 meters per second and you slowed down to a stop, then you would say final minus initial is 0 minus 25 because your final would be 0 if you came to a stop. So 0 minus 25 would give you negative 25 east. And what is negative east? It's west. So it goes the opposite direction if your acceleration is a negative value. Okay, it goes opposite the velocity, which is like this right here. All right. Now, so that's all the math stuff, but there's still some stuff I want to talk about with acceleration. And the first thing I want to talk about, if you'll switch to the second page, are falling objects. Now, we'll actually talk about this more, I think, in chapter 3. And, but I do want to mention it here, that objects on Earth that are falling, and the only force acting on them is the gravity from Earth pulling them down. We say that they are in free fall when gravity is the only force acting on them. So if I go outside and drop a ball over the side of the balcony, once I let go, then the only thing acting on it is gravity, and it will be in free fall, okay? And here's the thing. All objects in free fall have the same acceleration due to gravity in a vacuum. That just means in the absence of air, all right? On Earth, that acceleration has a value of 9.8 meters per second squared. So if I take a bowling ball and a golf ball outside to the balcony, I hold them at the same height, and I let them go at the same time, they'll both hit the ground at the same time. Doesn't matter that the bowling ball's bigger. They'll both have the same acceleration, and therefore they'll hit the ground at the same time with the same speed. Okay? Now, on the moon, because it's a different planet and has a different amount of pull for its gravity, the acceleration is a lot less. In fact, it's only about 1.63 on the moon. I call it slow motion on the moon. On Mars, it'd be about 3.8 meters per second squared. Okay? This is the increment. This is the increment you add to your velocity every second you fall. So if you start from rest and fall, every second you're going to add an increment of 9.8 to your speed. So at the end of the first second, you'll be traveling 9.8. At the end of the next second, you'll be traveling 19.6. Get the idea? You just add 9.8 for every second of fall to see how fast you're going. Okay, in any case, we'll talk more about that in chapter 3. Now, let's talk about motion in 2 dimensions. What we've just been talking about basically is linear motion, motion along a straight line. But not all objects walk along a straight line. A lot of times they travel in curves. Okay, so we're going to look at 2 different ways objects can travel in curves. All right, in the case of an object traveling in a curve, that means you're in 2 dimensions. In other words, you've got motion in both the x-plane and the y-plane at the same time, and they have to be treated separately. Okay? In fact, in physics, we do this a lot. We treat the math separately. We look at the motion in the x-plane, and then we look at the motion in the y-plane mathematically. Let's talk about circular motion. When an object is in circular motion, very similar to the picture on the front page, we know that it's accelerating because the direction of the velocity is changing. Now, the magnitude, the numerical value may not be, but if the direction is changing, you still have an acceleration. In fact, for an object moving in a circle, we call it a centripetal acceleration. A centripetal acceleration. Okay? So here's what it is. It's an acceleration that produces a change in the direction of the object's velocity rather than the numerical value of the velocity. All right? So here we have a carousel, and these are the little horses that are going around on the carousel. Notice the velocity is always tangent to the circle, because remember, an arrow is a straight line. So it's always tangent, and it points a different direction every point in time. Now, you're changing from one direction to another. Watch this. Here's this arrow, And we know that acceleration is defined as a difference, a subtraction of velocities. When you subtract two velocity arrows, you put them tail to tail. So I'm going to take this one and I'm going to slide it back and I'm going to redraw it right here. Or try to. There it is. Okay, same direction. See, that way. But I've got it tail to tail with this one. Now I'm going to draw between the tips. And look, where does this arrow point? That's the resultant, or the result of subtracting those two arrows. And look where it points, towards the center. This is the centripetal acceleration. Okay, that little arrow represents they've got them right there in the blue, but I wanted you to actually see where it comes from. Watch this one. This is kind of cool. Watch this. I am going to, let's look now at this one. If we change from here to here, all right, I'm going to bring this one back and put its tail on this one. It points straight to the left, just like this. So now, we start at the first one, draw to the second one, and look where it points. It points to the center again. So the acceleration always points to the center. Let's look at this. Since the change in direction is towards the center, the acceleration points towards the center also. Circle that so you know. All right, the velocity is tangent to the circle, but the acceleration points towards the center, because it's changing the direction of the velocity. All right, so that's circular motion. Now let's look at another motion, projectile motion. Now projectile is an object that you somehow toss or throw or fire or otherwise project into the air in some manner. For example, we have a girl there who's shooting a rubber band with her finger gun, okay? And when she does, she gives it a horizontal velocity. Notice she's pulling it back horizontally. So when she lets go, it's going to fly forward in a horizontal direction. But then, after it leaves her hand, it's also going to start falling due to gravity. It's going to accelerate down. Here's the cool thing. Once it leaves her hand, the horizontal motion stays constant. Look here. This arrow doesn't change. It stays constant. That's because gravity is vertical, not horizontal. It can't affect horizontal motion. And therefore, it's independent of that motion. It doesn't affect it. The horizontal motion stays constant. Gravity only affects vertical motion. So it starts with no vertical velocity. Gravity makes that velocity get bigger and bigger. Now, because you have one arrow that's staying the same and another arrow that's getting bigger and bigger, it makes the path curve instead of straight. Isn't that wild? It makes the path curve. So you have motion in the horizontal plane and you have a motion in the vertical plane. And the two added together give you a curved path. Isn't that wild? Look at this. You all are more familiar with this. Watch this. Here's a football. All right, so suppose at kickoff, the kicker kicks the ball. We know it goes up, and somewhere downfield it comes down and lands on the ground. Let's assume it lands on the ground for our purposes anyway. Okay, I'm going to mark several points I want to look at, the very tippy top point and the end point, and maybe a couple in the middle like this. All right, now, when the kicker kicks the ball, he gives it a horizontal velocity and he gives it an upward vertical velocity. So, of course, the ball starts moving forward and it starts moving up when it leaves his foot. Now, because there's no other force acting on the ball as it travels in the horizontal plane, there's nothing to change the horizontal motion. The horizontal motion stays constant. So I'm going to draw the same arrow to represent that motion right here. It stays constant. But gravity acts on the ball in the vertical plane. And since the ball's going up and gravity pulls down, it's going to make the ball slow down until right at the top, it's 0. All right? The vertical velocity at the top is 0. Only the horizontal velocity exists. Then gravity, at this moment, gravity changes the direction of the vertical velocity. Now it starts back down and it increases the velocity symmetrically. In fact, when it hits the ground, it should be traveling vertically just as fast when it hits the ground as it was when it left the kicker's foot because of symmetry. Okay? So, the two motions, the constant horizontal motion and the vertical changing motion, create a curved path. Now, if the vertical motion didn't change, it would be a straight path like this. But since it is changing, you get a lovely curve. Okay? In fact, we call it a parabola. Okay? That's the shape. I don't know if you've talked about parabolas in math, but that's the shape. It's a parabola. Okay? In fact, here's another picture right here. This shows the red ball is being dropped at the same time and from the same height that a blue ball is projected horizontally. And notice that at each point in time, they have fallen pretty much the same distance. Okay? That's because gravity is independent of the horizontal motion. It doesn't affect the horizontal motion. So both balls actually have the same vertical motion. They both start from rest, and they both begin to accelerate down with increments of 9.8 because we're on Earth. And therefore, they're going to both hit the ground at the same time. Now, the blue ball will be out here somewhere because of its horizontal motion, but it will hit the ground at the same time as the red ball. It really will. And I'm going to show you some little video clips about that so you can actually see it happen. Okay? All right, so the horizontal motion of the blue ball is constant, but it doesn't affect the vertical motion or vice versa. Neither motion affects the other. All right? So the blue ball will actually accelerate at the same rate as the red ball, and they'll hit the ground at the same time. Okay, that's about it. You're going to have a couple little video clips to watch today also to show you this right here because it's kind of cool, guys. And I'll talk to you later. Bye-bye.